The next session. So I am Beth Willman for the time being. Beth is off doing important things in a room or two away, talking to important people. So we're going to have a series of 6 talks on various aspects of data management, and those of you who may be calling in from Blue Jeans, the connection has been a little bit flaky. The slides are all available on the agenda page, so it may be that the slides may not work, but if we're lucky, the audio will still work. Let's go ahead and get started. Colin Slater will be the first speaker, and each speaker will get 15 minutes to keep us on schedule for lunch. Yep. You're all set. Just close the.
Okay. Hi, I'm Colin Slater. I work in the LSST Data Management Science Group at UW with Mario Jelko and Melissa Graham, and I'm going to give you the level 1 discussion, so alert production, nightly processing, all these names that we give it, up through producing the data products, and then Andy's going to take over and discuss getting the alerts to the users. I'm going to spend the first part of the talk giving you sort of the end-to-end brief overview of the pipeline as it's structured, and then we'll give you kind of a deep dive into some particular aspects that we've been working on in the past year. So the goals of level 1 are very simple. We need to find anything that changes by more than 5 sigma between the template image and the science image that we just took. We call these DAA sources, DAA for difference image analysis. I'll use that acronym sort of repeatedly. And the goal is to find it, measure it, cross-match it with any previous detections at that spot, and deliver it as an alert to the user within 60 seconds of the shutter close. So the goals are quite simple, and it's just the implementation that takes some finesse. So this diagram lays out all the stages of this processing that needs to happen in that 60 seconds, starting from raw data at the top to processed data products at the bottom. I'm just going to work through this top to bottom. The first stage is single visit processing. This is all the stuff you think of when you think of any reduction of images, so bias subtraction, flat fielding, astrometric, photometric calibration. All of this needs to take place to give us a calibrated image, and it gives us a set of sources that we use for that calibration. But these are really internal, and so we're going to focus more on the difference imaging for the science results. The next step after having a calibrated exposure is to do this image differencing. That's really the core of the pipeline, this sort of the very tricky bits of producing the alerts. So we need to take the templates. These were generated in data release production at some previous time. We need to make their PSFs match the PSF of the incoming science exposure. So we do this by building a convolution kernel that will do that matching, convolve the template image, and then do the subtraction. This gives us a difference image at the bottom. Once we have a difference image, we find any sources that change by either positive 5 sigma or negative 5 sigma. Then we must measure those sources. This is basically a reduced set of the measurements that we perform on any direct image, so fluxes, positions, etc. We associate that into DAA objects. So a single appearance of a source on a single visit is a DAA source, but then you want to be able to create a light curve of any other previous appearances of this source over the past visits. And so we link these into DAA objects, or we link them in solar system objects if that's what they are. We also take any DAA objects that were already known about but did not produce a new source in this image. So you had something that was varying on prior visits, but for this particular visit it does not show up. We still measure what is the flux at that exact position, just so that when you go and create a light curve of that DAA object, you don't have gaps where a DAA source did not appear. You still have fluxes, even though those may be close to the background level. And then this all gets sent to alert generation which is Andy's talk after this. And so the takeaway from this set of slides, from this part of the talk, is really that this set of data products at the bottom here, DA objects, DA sources, and DA force sources, are really what you want to be thinking about when you're thinking, how do I do my science with level 1 outputs? This is what is delivered to the user. So that's what we think about a lot. So that's the extremely, extremely brief overview of the level 1 pipeline. Now I want to go into some work we've been doing, actually exercising this pipeline and trying to test it from end to end as much as we can. So any image differencing survey has to deal with the problem of false positives. So any type of non-astrophysical transient events, so optical effects, sensor effects, imaging artifacts that we didn't successfully remove, cosmic rays that we didn't find. These all contribute to false detections that we would like to eliminate. And in previous experience, these false positives generally dominate the true sources of transients by a large factor. So in LSST, we expect actual transients on the order of hundreds up to about 1,000 per square degree. And the prior experience has been that on these precursor surveys has been false positives in the sort of thousands to 10,000 per square degree regime. And so we need to know how do we mitigate this problem, and that requires actually testing the LSST stack on existing data sets to know what's the best strategy for that. So for this reason, we've been exercising the level 1 pipeline over the past year. We're using existing DECCAM data that was taken as part of a near-Earth object survey, so they give us the repeated visits in the same part of the sky that lets us do difference imaging. We take the raw data, we run it through all these stages of the pipeline that I just described, through single frame processing, through image differencing, through force photometry, ingest that into a database, and then we run the initial stages of the moving objects pipeline, MOPS. And our goal here is not just for this to be a technical demo. We're not trying to show, oh, we can move data from stage 1 to stage 2 to stage 3. We actually want to use this to evaluate the scientific performance of the pipeline, so we know how to improve it in the years to come. So this is a visualization of the result that we get from doing that analysis. So we see we get the detections in this regime that we were talking about before, of the sort of thousands, 10,000 per square degree, 10,000 per square degree level, which is not what we expect. And we can plot the signal-to-noise ratio of these detections, and you see that there's this steep ramp-up starting at around signal-to-noise of 6 to signal-to-noise of 5, where all of a sudden we get this massive increase in the number of detections at low significance. And so this is not what we expect from just random fluctuations. We have Gaussian noise in the pixels, so we know how to compute what that should contribute in terms of false positives. That's what the blue line is showing. Really, you should not see that ramp up until signal-to-noise of 5 and lower. That's why we only detect a signal-to-noise of 5. But we get this strong ramp up at a higher level for some reason. We can check the outputs of the pipeline by kind of working around the image differencing part. And we can say, well, I have this input image that's the template, and I have this input image that's the science image. And I can say, I have a DA source. I'm going to go measure the flux in those two input images, and the flux in the difference image better be equal to the flux in the science image minus the flux in the template image. So we know from the inputs what the ideal output should be if all of our codes were perfect, and so we can plot the signal to noise from that analysis on the same scale. And so you see is that this massive increase in false positives are actually occurring more as signal to noise of 4, 4.5. And it fits the profile that we expect from Gaussian random noise. But for some reason, the stack is reporting that the significance of the detection is much higher. So we understand what causes this. This is the result of correlated noise in the images after we've done the PSF matching. So when we take a template image, we convolve it with a matching kernel. That's essentially a Gaussian smoothing operation. And Gaussian smoothing operation lowers the per pixel variance in that image. but it doesn't eliminate the noise. The noise is still there on PSF size scales. So we still have to, the noise is there, but we're no longer tracking properly in the individual pixels that level of noise. And this is a complicated problem because now, instead of each pixel being an independent sample, you have every pixel talking to its neighbors and makes estimating the noise much more difficult. And standard software just does not deal with this. There are a few solutions to this. One is to track the covariance matrix. This is theoretically n pixels by n pixels, but there are ways to make that more manageable. That's a possibility. You can do that either and save that on the files, or you can do that on the fly, or a method that we've been looking at recently is convolving this with what we're calling a decorrelation kernel. This is essentially to remove that excess power on the size scale of the PSF that we had inserted by the matching kernel. And this is just some math that you can look at in the slides online. And there's also a link here to a detailed description of all of this analysis at DMTN 21. These are the tech notes that the data management group writes. So this is another way of looking at those detections before applying the decorrelation kernel. It hid my title. So the x-axis is what we know the signal-to-noise ratio should be for these detections, and the y-axis is what we're actually reporting. So anything that's left of the signal-to-noise of 5 is stuff we don't want. That's all junk. We only want to detect above signal-to-noise of 5. When we apply the decorrelation kernel, that massive peak of excess detections is basically eliminated. There's still superfluous stuff scattered around, but the bulk of the detections that we're getting now are above 5 sigma, right where we want them. They're in the sort of 1-to-1 range, again, right where we want them. And the biggest deal is that we do not have this giant number of detections that we don't want. So this reduces our detection rate from sort of 20,000 per square degree down to several hundred per square degree, which is what I was saying was the expected number of actual transients in an LSST-like survey. So this is putting us much closer to a sort of 1-to-1 regime rather than a 10-to-1 regime. The other great thing about this is that sort of the most sensitive customer of the alerts is the moving objects pipeline. Because of the way you have to link multiple detections together, if you add lots and lots of excess detections, that linking becomes extremely difficult. And when we eliminate this large number of excess detections, that puts us in a regime where we've actually tested MOPS. We know MOPS can handle this level of false detections without applying machine learning sort of right on from the get-go. And just to kind of prove that statement, this is a selection of postage stamps that I made just from the output of MOPS. So 3 different epochs are red, green, and blue, so you can see actual asteroids moving in these postage stamps. And this is not something that I selected by hand. This is just a representative image that the MOPS pipeline produced. So we're looking really good. And just to sum up, we have a theoretical understanding of the correlated noise problem, and we have a principled solution for how to handle that in the stack. We have that implemented in the LSST software, and we have it demonstrated on real data. The reduction is basically an order of magnitude in false positives, and that puts us in a much better regime without the need for strong post-filtering and lets us run MOPS. So, thanks.
More interested in the second half, but I have a question about something you shared at the beginning.
Sure. Tell me when to stop.
Yeah, that's good. So in one of your 4th bullet down, you said you want to associate one of these transients with a known solar system object. So is that, how do you do that? You're going to calculate every orbit for every known object, give you a 60-second interval, and say, oh, that's the one.
That part can be pre-computed, so we call that, or we've started to call that ephemeris generation, where we know sort of ahead of time with some handful of minutes lead time that we're going to be pointing towards this point of the sky, and so we can go in and compute for all the known objects where they should be in the focal plane, and so we kind of have a subset from which to associate without having to do everything inside of 60 seconds.
away most of them because only a small number in this cone. But you probably noticed that most solar system objects have very poorly known position. So it might be 50 arc seconds away from where you measured it, and that's not going to show up as a positive place.
Yeah, and so that ephemeris generation part is to take care of the really obvious causes. Sure. But then, so if we don't get a successful linkage there, we can always come back during the day when we do the full solution to find new objects. That might also be opened up to a sort of a wider matching radius for already known objects.
So, could you comment about how this level 1 processing and identification will work in very crowded fields, which are outside the wide path speed, but are still kind of things that you expect it's going to work well?
So that is actually what we are working on right at the second. So we have a set of transient search that was done in the bulge, and so I've been working on that data right now. The challenges are basically getting astrometric and photometric matching and fitting to work, and then we're hoping that the difference imaging takes care of the sort of confusion problem, and so we hope we don't have to deblend difference images.
It's time for
So Colin gave a really nice introduction to how we're processing the data to actually identify the events on the images. What I'm going to do here over the next 10 minutes or so is to talk about what are we actually measuring, how are we distributing those events to the community, and what you can expect in terms of your ability to access the LSST events. So what I thought I'd do is I'd start out by talking about what are the objectives of the alert system, right? So the goal that we have is to transmit nearly everything that we know about about one of these LSST events, to enable the science community downstream to be able to run their astrophysical classifications, to essentially to determine what events need prompt follow-up. And the prompt follow-up or prompt attention is the important aspect of this, as I'll come back to as I go through the talk. And so this means for follow-up observations for classification, to differentiate between classifications, and also just in terms of a discovery or identification of a new event. We will provide information on classification, but only classification on whether it is an astrophysical source or not. So not on whether it's a supernova, RR Lyrae, or some astrophysical event, but just on the nature of whether it's spurious, whether it's real or bogus, and that's the objective. And then the goal for all of this is to provide all of the information that we know about these events within 60 seconds. So what does this mean in terms of numbers? Well, every 39 seconds, we're going to be detecting a varying, transient, or moving source. We expect to detect about 10 million of these over each night. And so if you calculate the number of visits, that means about 10,000 per visit, or about 50 real astrophysical events per CCD. And as we process in units of CCDs, you can expect to have kind of groups of 50 events coming out, and 189 of those groups of 50 events every 39 seconds. Right. The alerts themselves get transmitted over a wire, so they get transmitted to various event brokers, but they're also stored within a queryable database. And this means you can actually come back to those events on subsequent days. Something that is not, I think, fully appreciated is that all of the variable and moving sources are also reprocessed during the data release processing, the DRP. And this means the DRP will have better access to the photometric calibration and all of the history of the observations. And so if your interest is in variability, then the DRP processing may provide you the most accurate light curves, as opposed to needing information that needs prompt attention for example, for follow-up. So what do we expect to put in an alert? The details are just at the cutoff at the bottom of the screen. It's ls.st/dpdd, which is the data products definition document. This describes all of the measurements that we're going to be making and releasing as part of the alerts, and in fact as part of the DRP. How we're actually going to make those measurements is available at ls.st/ldm151. Both of these documents are being revised at the moment, the revision is expected to be completed by about the end of September. So if you want to get the details, you should go to these two documents. Just to give you a kind of an overview of what we'll be measuring, for every source that's detected, we measure unique ID and timestamps. From the difference images that Colin introduced, we measure positions, shapes, PSF fluxes, or trail PSF fluxes for moving sources, together with their uncertainties. We have, as I mentioned, a measure of the spuriousness of the event, whether it's real or bogus. And then we also have cutouts. So on average, about a 30 by 30 pixel image. And this cutout is of the template that was subtracted from the image, and also of the difference image itself. So that's the measurements on the actual events, or the data that we take on a particular night. We also report the history of that event. So all of the previous DIA objects that can be associated or matched with that event that was detected are packaged and released, and also characteristics of the variability that you might extract from the light curve. And this, the measures of variability that we're currently considering, you can find in LDM 151. And then the last thing we also put out is a measure of the environment around the event. So we have a link to the nearest objects, so objects that would be measured not in the difference images, but in the real images from the DRP. We currently are providing three, so pointers and distances to the three closest objects around any event. And that gives you an estimate of what the environment is around these events. If you put that together in terms of the data that we're producing, and also the 10 million events per night, this means that we're generating between about 400 and 600 gigabytes of data for a full alert stream. The data themselves get packaged up in VO events. VO event is a standard protocol for announcing alerts to the community. It's an XML-based standard, and this also means that because it's XML and it's textual, this means that this is not a particularly compact protocol. And so what that means is that if you're generating 400 to 600 gigabytes for a full LSST event stream, then it's likely that the majority of users will not want to have that full stream coming out. They'll be interested in subsets of the attributes that are measured, or subsets of the sources themselves, right? You may only be interested in the brighter sources. And so this means that we need to provide a hierarchy of access mechanisms. The three levels of kind of access mechanisms that we're going to be providing include external value-adding systems, and this is examples like Antares, which is an event broker that's been developed at NOAO, and I think will be part of one of the breakout sessions over the next couple of days, in fact, two of the breakout sessions over the next couple of days. These will be validated and tested systems that are capable of ingesting the full LSST data stream, and they will be able to provide additional information, so cross-matching with other external catalogs, or maybe doing machine learning for astrophysical classification. The nice thing about the protocol for VO events is that these systems themselves, these external brokers or value-added brokers, can actually also stream out the VO events. And so you can actually connect directly into these, and this gives you a cascade effect of brokers serving, multiple brokers serving the community, which limits the impact on the bandwidth associated with the LSST service. What we as a project will be able to produce is a limited LSST filtering service. And this means, essentially, and I'll show you a diagram of this in the next slide, this means a set of agents that are configurable. Configurable meaning that you can limit the attributes that are coming out. So you may only be interested in the flux of the actual event and maybe the previous event, or the closest object in other DIA object in time. You may only be interested, you may not be interested in the postage stamps themselves. And so we'll be providing this limited filtering service which will have agents. These configurable agents will enable you to limit the types of attributes that come out, or the limits on the brightness of the sources. These will all be available. You'll be able to access these data streams or these filtered data streams using standard VO event clients such as Comet, and we will be requiring authentication to connect to these streams. And the reason that we need the authentication is to be able to track the actual resources that are being used and make sure that they're managed appropriately. The third access mechanism will be to the historical events. Now, historical events just means what's happened in the previous 24 hours. So within 24 hours, we will have an alert database that will have all of the events from the previous night. And so that will be queryable, and that will be an example of how you might want to go back if you're actually trying to learn how to train a machine learning algorithm for a particular classification. Yeah, I'm good. I'm on time. The actual delivery system itself is in design at the moment. If you have particular use cases that you want to know whether we can actually support, I'm very happy to talk about that over the next couple of days, and particularly in these broker sessions or breakout sessions that we're having for the next couple of days. But just to give you an idea of the design that we're working through, we have the DIA sources coming in, 10,000 events per visit. This goes into a message queue. The message queue, for those who are interested, that we're looking at the moment is Kafka. This message queue allows you to rewind events, so you can look back in terms of the history of the event, history of the stream of events coming off. But the information that comes from these message queues goes to these alert agents. Some alert agents will be fully configured, so they can take the full data set, going, for example, up to Antares, or they will go out to the alert database where we'll actually store those alerts for subsequent querying. Or they may go down to these configurable filters that allow you to filter the attributes that are coming off, the attributes that you want to serve from the event. These will then be connected to standard VO event clients, and this dashed line represents the boundary between what is operated on in terms of the LSST systems and what is operated on from external brokers or external clients. The important thing to remember here is that that by doing this filtering, that if you said, I was only interested in 20 events per visit, or you said that I only was interested in 40 numbers for each event, that would mean for the same bandwidth as serving out the full 400 to 600 gigabytes of data, you'd be able to support about 500 simultaneous users. All right? So this allows us to provide this hierarchy of access. So just to conclude, the alert system will provide almost real-time access to the data, about 10,000 events every 39 seconds throughout the night. These events themselves are world available. It's not, there are no limitations on the actual event data compared to the data release processing. The alerts themselves will be packaged to include all of the historical observations that we have, together with postage stamps of the images. We'll provide a hierarchy of access mechanisms, including a limited filtering service for filtering particular columns or doing small queries on the actual alert stream. We'll also provide access for the full data streams for external value-adding brokers that have been validated to demonstrate that they can actually serve and support the 400 to 600 gigabytes of data coming off. And then our expectation is that we will be managing the bandwidth by this filtering and the replication aspects of these external brokers, and also that we'll have a mechanism, if we need to, is to throttle this bandwidth depending on how many users are connecting and how much data is coming in. Okay, thank you. I'm sorry, can you? I see. So you're asking, can we have at least galaxies? So can we use the classification of the star galaxy classification of the sources so that there is a diversity in those three nearest neighbors? Let's take that offline and we'll talk about that in detail. At the moment, we're currently budgeted for 3 nearest neighbors, but we can talk about how we actually allocate them. It's about 50% goes in cutout and 50% goes in historical information. Yes, yes, we have thought about that, and there is actually discussion about how to evolve the VO event protocol itself. The aspect that we have is that we wish to support these external VO protocols, but there is discussion about that, yeah.
All right, am I audible? Yep, I'm audible. Okay, so I've written a lot of very text-heavy slides. The reason for that will become clear in the next talk. But I'm also not going to read all the text in my slide. A lot of this is information about the current state of the level 2 pipelines that DM has produced, mostly for people who might be interested in using it. And so there's extra information there that if you want to go back and read the slides later, or if you can read really fast while I'm talking, you can read that there. I'm going to sort of hit the major bullet points and skip over the minor ones in the interest of time. Also because it may not be interesting to everyone. So this is a diagram of what the pipelines we have right now look like. We start with single frame processing. This is essentially the same thing that's happening in the difference imaging that Colin talked about. This generates a source table, some calibrated images. We can then do what we call joint calibration. There's a couple different ways to do that right now. This updates the WCS and the photocal. We can do image co-addition. We make coads. We process the coads in various ways, and I'll talk about this in quite a bit more detail. This section over here, we actually write several different catalogs out when we process coads, but together they can sort of be seen as the predecessor of LSST's eventual object table, which will join them together. Each of those steps is a Python class. It has an executable script that runs it, so you can either run it from the command line, you can run it from within Python. We have code to parallelize all of these steps, or at least almost all of these steps, over big clusters. This is not the same sort of parallelization that we plan to do in the end. We're planning more sophisticated things that I don't know exactly what we're doing yet, because that's not my job. But we have something that gets us through right now, and it works well enough, at least for sort of the data volumes that we see today. All the data products we produce right now happen to be FITS files. It's not guaranteed to be that way in the future, although we'll have ways to export things to common formats like FITS. We also have a way of abstracting away the file system so that you don't have to deal with these things if you use our Python code to load things. And that's actually quite a bit more convenient. So if you do end up using our code, I strongly recommend using that thing which we call the butler. So first up, I'm going to talk about this single frame processing where we generate the source catalog and the calibrated images. This is pretty straightforward. We do instrument signature removal. That's, biases, flats, darks. This includes a brighter fatter correction. It's not the brighter fatter correction that we want to use eventually, but it's a brighter fatter correction, and I think it's about as good as anyone else is doing right now. Next up is what we call image characterization. That's basically PSF modeling and some other things needed to support PSF modeling, like finding the stars you'll use to do PSF modeling. And then we do calibration, in which we match to an external reference catalog, compute the initial WCS solution, the image registration, and do an initial photometric calibration. After that, we'll move on to joint calibration. And that's so in each tract. So a tract is an area on the sky, a larger area. We don't know exactly how big it's going to be yet, but it's sort of the scale of an LSST visit or larger. So all of the visits that are on this area of the sky, we fit jointly for a new WCS and a new photometric calibration. This is where we deal with the clouds and not quite perfect photometric conditions. It's where we use the density of stars that we get from having lots of dithered exposures to improve the quality of the image registration and our knowledge of the optical distortions, as well as the atmospheric distortions. This stage is not quite as easy to run as the rest of the pipeline right now. We have two things we're sort of transitioning from one to the other. You don't actually have to do it. If you did a good enough job with the initial WCS and photometric calibration, you can proceed to the next stages without running this. But this can improve the results quite a bit. So one of these solutions we have is called Mesh Mosaic. This came from the HSC side. Right now it only runs on Subaru data, which is one of the reasons this is harder to run. It uses dense matrices, and that makes it slow. It takes about a half hour to run this on 4 HSC visits if you only use a single core. And that means it doesn't scale as the number of visits go up. Joint cal is what we'd like to move to in the future. This was written mostly by Pierre Astier. It doesn't quite have the photometric fit implemented, and it only runs on CFHD and HSC data right now. But it uses sparse matrices, so it's much faster. So this is a factor of more than 60 faster, a factor of 60 times 3, 180. This is what we'd really like to go to in the future, and hopefully we'll have it up and running for everything pretty soon. Next up is image co-addition. So right now, everything the stack does for deep objects is on and off of coads. That won't be the case in the future, but it is how we do things right now. And we've put a fair amount of effort into our coads to make sure that the coads are good enough to do a lot of science from. More so than you might expect from most coads, although not as good as you can do if you do cleverer things or more brute force things that don't involve coads. And this includes for us, if you're looking carefully at the scripts you'd use to run these, we actually detect on coads as the final step of making coads, just so we only have to write coads out once. So in co-addition, it's pretty straightforward. We just resample images to a common coordinate system. This assumes Nyquist sampled images, so you can't use the stack right now on HST data because those images are not well sampled, and the algorithms we use to warp them aren't valid. Co-addition on undersampled data like HST is a much harder problem, and while it's doable, it's hard to fit it into this sort of approach. This creates a temporary image that's one for each visit that's in the right coordinate system. We combine those images, and now we have a coad. It's important, though, when you make a coad, not to do naive outlier rejection and not to do something like a median. When you do that, and your images have different PSFs, you get different statistical behavior in the center of the PSF than you do on the outside. And that means that you create a PSF, an effective PSF on the coad that is a function of magnitude, and there's not really a PSF at all. And those coads essentially become unusable. You either need to match to a common PSF and degrade some of your data before you make a coad, or you need to not do outlier rejection or any sort of robust statistic when making a coad. Nevertheless, you'd like to get rid of the garbage that's in your individual frames, the cosmic rays you may have missed, asteroids, satellite trails, ghosts, etc. And the approach we've taken to this is what we're calling safe clipping. And this works by we create a coad in which we don't do any clipping. That's this one in the middle here. We create another coad with a really strong clipping, with 3 sigma clip mean. It throws away a lot of good stuff, and it makes the PSF bad in just the way I said. We then difference those, and we look at where the differences are and trace them back to the individual exposures. And we reject any areas in which the rejected area only overlapped a detection in 1 or 2 exposures. So what this does is it says these are the areas where this particular exposure was an outlier. It finds them spatially within that exposure and then rejects that whole area. So that preserves the PSF on the coad, except at the boundaries where that happens. So if you actually did reject the PSF, reject a pixel from the final coad, the coad effective PSF is discontinuous at that point. It's well defined, but it's discontinuous. And we don't try to track the discontinuity in those PSFs. We do model our PSF as the sum of all of or the average of all of the PSFs of the input images, but we don't try to catch those individual missing pixels. But we flag those pixels so you can know at least that your PSF is slightly inaccurate and throw away those objects from your catalog if you care deeply about accuracy of the PSF, as you might in, say, weak lensing. And as you can see, this approach is actually much better at just cleaning stuff out. It's not just better for handling the PSF, it actually catches more. This is probably not what we'll do in the end. It's a good placeholder. In the end, we'll actually just be using difference imaging of the sort Colin described to find these artifacts, mask them out into individual images, and keep them out of the coads that way. Moving on to our coad processing scheme. This is how we build the object table. And we do it in 5 different steps. And this is a bit of an artificial, temporary artifact of the fact that we don't have a good way to process all of the images from all the different bands in memory at once. Eventually, we'll have better parallelization mechanisms, and we'll be able to use more cores, and thus less memory per band by parallelizing at a lower level, or we'll just have more memory per core. But this works moderately well right now at producing a consistent catalog across bands without actually having all the image data from all bands in memory at once. We start with detection. We detect separately in every band. And what this generates is what we call a set of footprints. These are regions of the image that are above threshold and peaks within them. All right. We merge detections. And then we deblend them separately in every band. So we have the same definitions of where objects are, but we might choose different pixels, different assignments of pixel values for each of them, and then we measure separately in every band. We then choose one band for each object to be the reference band, and we go back and measure again. And this is what we call force photometry. We're using the same centroids and shapes across all bands so you can get consistent colors. So this is the diagram I've just talked about. It's not the diagram we'll have in the future. This is my first take at a diagram from the future. Don't try to read it. You'll hurt your eyes. And also, it's almost certainly wrong in many ways. But it's sort of our best guess at how much more complex things will get. So the overall state of the pipeline, this is the highest quality general data set pipeline in astronomy. There's some big qualifications on that. It's not as good as a single purpose pipeline for a specific science case. That people can construct for specific science cases. It's not as good at processing other individual data sets, but it does work on lots of data sets, and it does work for a lot of different science cases. And that's the kind of thing LSST needs to build. One of the big challenges for LSST is not just doing something that is good for detecting high redshift quasars or doing weak lensing. We have to make a single catalog that works for both. And that's harder than you might think, because people want to make different approximations, and that means we're not actually allowed to make a lot of those approximations at all. Our deblending is not so great. If you want to learn more about this, come to the next session. I'm going to blow through faster than I had before. PSF models, it's working moderately well, sort of as well as anyone else's PSF modeling is working. We're delegating most of this to the PSFX code that Manuel Bertin wrote, but we want to move away from that in the future. Galaxy photometry is kind of at the SDSS level. We do galaxy fitting with the C model approach. It's a bit of a hack, but it's been demonstrated to work pretty well in practice. Crowded fields, we have not tried to do crowded fields at all yet. So if you're a crowded field astronomer, this may work if it's not too crowded, but it's in no way an indication of how we do in the future. And again, I'll talk about that more in the next section, one of the breakouts on blended objects. Galaxy shapes, we also have not tried hard on galaxy shapes. We have the ability to run the old HSM regaussianization, which is battle tested and robust and quite biased because it's been around for a while. But you can still learn a lot from it. And it's quite fast, which is nice. We don't have a harness for doing multi-fit and other kinds of more advanced modern shape measurement yet. If you want to use this code, it really works well if your data comes from one of these cameras. It's a lot harder if it doesn't come from one of these cameras. If you do want to use this code and it doesn't come from one of these cameras, talk to us. We can help you write support for it, but it's not a small job. And there's a tutorial here you can check on later. If you have small simulated data, you probably don't want to use these pipelines. You probably just want to use our code as a Python library. And that's it. The next talk from Paul Price will actually show you all the pictures I didn't have, because we've developed a lot of this for the HSC pipeline, and we've been running on the HSC pipeline, and that's what Paul will be talking about. So that's it for me.
Paul, are there any questions?
Let you take the question. All right. I didn't see a question, actually.
Any questions?
All right, we'll move straight on to Paul. Oh.
Is that you? Yeah.
If the space-based data is well sampled, then it's very easy. I'm not immediately aware of any sort of optical near-IR space-based telescopes that are well sampled. And that makes it hard. Well, you can do a lot of this stuff, but you cannot make coads. And I think the PSF modeling will require a little work too.
Very good.
Do I need the mic?
Oh, yep.
You don't want to take that with you. All right, I have the privilege, again, of being the front man for a lot of very talented people, a lot of very hardworking people. As I said, I'm really just the front man, and I'm taking I guess the credit. But this work has been done by the group at Princeton in collaboration with people in Japan, both at the IPMU and the NAOJ facilities. So this really happened, this started several years back when I think LSST was kind of underway, and Robert and others had the great idea. Let's take what we're developing for LSST and apply it to HyperSupremeCam. And the idea there was that you would get, you could leverage the effort being expended on DM, and then you could use the experience from running it on HSC. And putting these together, you'd have a far more powerful pipeline than either could write by themselves. So let me introduce first HyperSupremeCam as an LSST precursor. Here's the HyperSupremeCam being, it looks like it's being installed at the Subaru telescope on Mauna Kea. This thing is absolutely huge. It stands taller than a person, and it's made of ceramic, which is very brittle, and you don't want to bump it. So they take very great care as they maneuver it over the telescope. So there's several lenses in here, and the light ultimately falls on this focal plane array of 112 CCDs, 104 of which are being used for science. The whole camera has about a quarter of the attendu of the LSST camera, but it's actually operational now. Now, the 1/4 number is a little bit misleading. In my old life, I was part of Panstar, so I'm used to the battles about attendu. But you have to take out of this number, the fact that this telescope is not surveying every night as LSST will. So, if it's operating something like 1/8 of the time, it's maybe a 30th of an LSST. But it is giving us a snapshot of what LSST might do right now. Here's one of our first light images. Of course, if you've got a big wide field camera in the Northern Hemisphere, you take a picture of Andromeda, and there it is in all its beautiful detail. Unfortunately, one of the big problems that we're having with this camera is it's sitting on an 8-meter telescope, and it's just too bloody big. So the core here is well and truly saturated here and here. You can see. And so that has pushed us to certain regimes in data processing where we used to take things for granted. For example, in SDSS, where you assume just about many things that you look at are stars. We're going so faint that the galaxies are mixing in there, and PSF estimation is more difficult. Anyway, so with this wonderful, powerful camera, the community decided to undertake a strategic survey program, 300-night survey in the regular broadband filters, and because Japan does it so wonderfully, there's a bunch of narrowband filters there as well. It's a traditional wedding cake survey design, 1,400 square degrees to a moderate depth. There's there are 4 deep fields spread across the sky going somewhat deeper, and then there's 2 ultra deep fields. These are single pointings where just stare at the thing as long as we possibly can. So here's the survey areas laid out on the sky. Here's the deep fields, Elias N1. I've forgotten exactly what that is. And there's one here. Cosmos, of course, is included. Cosmos is an ultra-deep field, and then the other ultra-deep field, I think, is the Supreme Chem Extragalactic Deep Survey or something like that. So as you can see from this diagram, this is a very competitive survey happening now. We're not going quite as wide as DES is, although we're going deeper and with better point spread functions. As you can see here, here's some example seeing histograms. This is a tad misleading because we are taking I-band data in the best of conditions. If it's predicted to be good seeing, we're going for I-band. So that's why this is so much narrower than in the R-band. But we're getting absolutely exquisite quality images. In fact, one of the problems that we're having is that the image quality is just too good. And so that in some images we're undersampled, and we run into the problems that Jim was alluding to before, and we're having trouble modeling the PSFs. It's a wonderful problem to have. Absolutely. All right, so we've taken the LSST data management stack and are applying it to Hyper Prime Cam. This is our primary way of reducing the data. In fact, I was just outside with Jean Magnier, and he was talking about using Pan-STAR's IPP to reduce Hyper Supreme Cam data. That's the first I've ever heard of other people reducing our data with something else. But this is the primary means, and especially for the strategic survey program. This is my view of our pipeline. It's simplified compared to Jim's diagram, but you can see here that each of the pipeline stages maps to scientific goals. For example, the single frame processing is good for bright unblended transients. Stacking, if you're interested in single band science, wallpaper science. There's this forced visit measurement is good for light curves of unblended sources. We don't yet have multi-fit. There are prototypes available for that, but we're not running it at the moment. The image differencing code is, we do have what's been developed for LSST as of a few years ago, and that seems to be working just fine out of the box for our work. Naoki Yasuda reports it's doing just very nicely. Thank you very much. So we're reasonably happy with the quality of the pipeline data. So here's a few numbers. We're doing about 1.5% PSF photometry. We're aiming for 1%, but at the same time, these numbers don't take into account this is from comparing two exposures and seeing the noise in the PSF fluxes between those. If you take off the square root 2 discount, that is just shy, like within this much of our 1% goal, and that's the same for most. And we are our differences against Pan-STAR's 1, which we're using for calibration. Probably some of that is also coming from Pan-STARs as well. So we're reasonably happy with what's coming out of the pipeline, and it certainly has been good enough to be able to do some science. And I think there's about 7 or 8 papers from HSC now that are if not submitted, then at least circulating around the collaboration, about to be submitted. Here's one from Matsuoka-san, who has been leading the charge on high redshift quasars. And one of the annoying problems is, again, that this telescope is just too big. And so here's a histogram of what we're finding. And you can see these blue boxes are quasars. And we're actually starting to run into getting contaminated by these Lyman break galaxies. It's really annoying. So here's the wonderful progression up to a redshift 6.8 quasar. He's doing some great work. Here's the Eye of Horus, so-called, by Tanaka-san. Is a strong lensing system. Here's one from Anaprita Moore. It's about to be submitted soon. James Chan is doing I think this one, the Eye of Horus, was identified by a high school student or something looking through images. James Chan is taking an automated approach and looking for strong lensing systems. This is also a nice system for doing dwarf galaxies. From the Hyper-SupremeCam survey, here's a Milky Way dwarf galaxy, rather faint, that has been discovered, and it should be out public soon. Here's some work I'd also like to advertise that we did with Jeff Carlin, Beth Willman, looking at dwarf galaxies around nearby galaxies. And again, this one was identified by eye. But I think this one was an automated approach. Jim already mentioned that we've been putting a lot of work. Not only have we taken from LSST DM, but we've introduced a lot of the features that have recently found their way back into the stack. Many of the features that have appeared on the stack in the last, year have come from development for HSC over the last few years, including bug fixes. We've got a bunch of documentation that can be pulled over, QA, all that sort of thing. So I think really HSC and LSST going hand in hand is really a win-win situation, and I hope it makes LSST a lot stronger, and certainly LSST has made HSC a lot stronger. I thought I would show, just because I can, the one to the left, he says. Okay, so this is done by the group out of NAOJ. They've taken all our images and put them on one of these scrollable maps. And I know Robert and Michael love just panning around through here. The multicolor images displayed like this, as Robert has said before, really bring out all the annoying problems. Of course, we're doing that safe clipping, but here's something that we managed to miss. We need to do a better job of saturation trails. As we go around, we'll see all kinds of ghosts and the like, asteroids that we haven't clipped out, but it's really an exciting data set. Let me stop there and open the floor to questions. Sir.
So does your data set, or perhaps a future data set, include Subaru data and sort of dense, low latitude fields that would be suitable for testing some of the issues that we discussed later?
I believe that there are people imaging galactic bulge-ish fields, looking for dream objects that might be hidden up there. And I think that is what Colin is working on. I can't see him. But certainly there are fields that are denser and we care about and are being run with our stack. So yeah, there's a lot there.
I didn't want to say anything about sky subtraction, background subtraction, whether as part of the pipeline you'll not be reducing, say, intercluster light.
It is, as Jim said, it's very hard keeping everybody happy. So there's definitely work that we need to do on sky subtraction. We're doing the plain dumb thing at the moment, and we have plans for doing more sophisticated background matching instead of background subtraction. It's one of those problems where one man's junk is another man's treasure, because your intercluster background light is going to annoy his weak lensing shape measurement. So we need to find a way to preserve both. And probably one way, and disentangling it from terrestrial sources and scattered light and all that is I'm sure you must know, is a difficult problem. But my guess is what we will do is subtract off what we can, do the best we can, and then preserve what our estimate of that sky is, and then you can get both or whatever you want, and you can say, oh, look, I don't like what you did here. In fact, this is actually in intercluster light, and you can go from there.
Let's move on. Let's thank Paul again. David Ciardi.
This is fun.
Okay. Can everybody hear me? Yep. Excellent. So for those of you in the back of the room, I can smell the food here as they bring it through. So that should just start wafting through. So Jonathan, you have a lot of pressure to finish before the food arrives. Okay. So for those of you who don't know me, I'm David Ciardi. I am the project scientist for the Science User Interface, and I'm standing up here can talk to you about the progress that we've made since the last time I presented at last year's All Hands meeting remotely. But while I am standing up here, you should all know that I am just the scientist. There's an enormously talented technical team for which I am talking for today. And so some of them are in the room. They're all here this week. So if you have other questions, please feel free to find them. And if you don't know who to talk to, please let me know. So just note that it's the work that I'm about to show here is certainly not my own. Okay, so the purpose of the SUIT is actually fairly simple, right? We want to be able to enable access to all of the LSST data products, some of which you heard about in the previous talks today, the level 1 processing, the level 2 processing. But we also want to be able to not just give you access to those data products, but we want to be able to enable you to visualize and explore the data. It's a very large data set, and so exploration is probably going to be very crucial, very particularly at the beginning of the survey when nobody has a clue what's actually in the data till you look at it. And then, of course, excuse me, provide an interface also to what has been called for this project the level 3 facilities, which is enabling sort of value-added processing and analysis next to the data by the users. The data are very large. You don't want 100 people dragging over 15 terabytes of data every night just so they can process it at their own place, right? You want to be able to enable people to work with the data at the source of the data. Not a problem which is just specific to LSST, but certainly something that we are paying attention to. So the philosophy that we're trying to do, and I presented this last year, is that we want to make this simple enough that the novice and the general users can be able to explore the data and look at the data. There'll be plenty of people who are not in this room who are going to want to use LSST data, and they're not even thinking about LSST today because LSST hasn't actually happened yet. But they will think about LSST once the data start flowing. And we want to be able to engage those users as well. But we also want to make the interfaces flexible enough and powerful enough to meet the needs of the experienced users, those people who really already know what it is they want to do, or have a very specific project, or they're the goal of what they need to do is already well defined. And so we want to be able to build this environment that fulfills the needs of these general users, right? A portal and a workspace environment. We want to be able to enable searching and image visualization and table manipulation and plotting. But we also want to make these components usable by others to build tools and environments that meet their own special needs. At the end of the day, what we're trying to do is create an environment that enables you, the user, to be creative and flexible, right? When I stand up here and I talk to collaboration members, it's very clear to me that there is no way that we can build one interface or one visualization environment that suits the needs of every user or every collaboration. So people who are doing solar system work really don't care about redshifts, right? So you don't want to worry about or build an interface that only is oriented towards extragalactic and redshift measurements, for example. So we want to be able to build a portal, but we also want to provide a set of tools and a workspace and a toolkit to be able to put these pieces together, either through the accessing the data through APIs and accessing the tools through APIs. And all of this is intended to mate the user with the data. So this is as a scientist, flowchart for how the system is going to be put together. This makes the engineers on the team twitch, but this is intended for you, not for them. And the idea here is, I'm going to use the mouse here in case there's people on blue jeans. Can you guys see the mouse? Yep. Okay. Can people in the back see the mouse? Okay. All right. So the idea here is that, behind some authorization layer, the LSST data will be available through some data access layer. This will be the images and the catalogs, and all the calibration data, all of the engineering data, all the alert databases, all of everything, all of the tables, all of the products that the project is producing will be available in some form here. And we want to be able to provide sort of direct access through the authentication layer so people can get to the data that they know that they want to get to, right? We don't want to get in the way of the experts who know, that's the table I need to query and this is the thing that I want to get to. But we also want to be able to provide a portal environment in which people can explore the data from sort of like what you would think of as a traditional web environment that you see in many of the archives in astronomy today. But here it'll be connected to, of course, the access layer because it'll have to talk and get through the data. But there'll be a data visualization server, which is an adaptation of a tool called Firefly, which I'll talk about in a moment, and also a workspace environment. And all of this is intended to be working together so that a user or a group of users, and here I've expressed sort of the collaborations as the little stick figures, or maybe one single individual person who's trying to do something on their own. But all of this is intended to work together so that we provide an environment in which you can explore the data, work with the data, access the workspace resources, the storage, the processing, a local, maybe database so that you can keep small local tables that you've produced through your queries or through the web interface. And so all of this provides an environment in which you can work and save and then come back to later. But of course, that's not everything, and I'm not trying to anticipate everything. And so what we really want to be able to do is enable users to be able to bring their own code, to build their own environments, to lay out a workflow that works for them and the collaboration that they're working with. And so the light blue box here is intended to represent that what we're trying to do here is give you an environment in which you can customize it, or give you an environment in which you can just do what you need to do because the basic tools are sufficient. And the reason that they're all connected is that at the end of the day, we don't want it to be one piece versus another piece, but rather maybe you're using the preset web portal for yourself, but then you have a very specific other environment that you've set up, and they're connected in some fashion. And then finally, at the very end of the day, as large as the computing resources are for the LSST Data Access Center, astronomers are excellent at exceeding those capacities and pushing the limits of what's available. And so the idea behind the SUI will be that it'll be installable and deployable in other environments. And we have to work through exactly how we're going to do that. But if you have a set of resources and computing infrastructure wherever you happen to be, maybe it's the cloud, maybe it's your own university, but that you can install it in that kind of area and then still have some kind of access in the same way, in the same kind of environment. We're trying to provide the community with the ability to access the data in a flexible way as possible. Yeah, all right. So I am like on slide whatever, so I need to speed up here. But so, you know, this is probably the biggest message that I want to get through. This is where we're going with this. So Firefly, what I talked about is our image visualization service that's already in use elsewhere. For example, at the Infrared Science Archive at IPAC. And what's really useful about this particular thing is the client-server configuration. So you can keep the data, the physical large amounts of gigabytes on the server in the DAC, but you only bring over the specific information that you need in order to do the visualization. And it includes table manipulation, plotting, imaging, and currently we just added histogramming. But what's really special about all of this is connected to each other. So if you do some kind of filtering on the table, it's reflected in the plot. Or if you do some kind of selection in the plot, it's reflected in the table or on the overlay on the image. It's a unified data model that's already functioning, that we already have. This is not vaporware that we're trying to write. It already pre-exists, and so we're adapting this to be used within the SUI. But then on top of that, we want to be able to connect all of this to some kind of processing and flexible environment, and there we've decided to make the connection to Python just because the community is moving in that direction. The stack has a significant fraction of everything it does in Python. The Butler, which is a tool to access files, is written in Python. So it's part of integrating all of this with DM as a whole. And so what we've done is we've started to connect the visualization tools through APIs to Python, but also the other direction is happening as well, where we can use the visualization tools to call a Python program or script or function, and then bring back that information and bring it into the visualization environment. And so we're starting to connect the capabilities of the flexibility of anything you can do in Python, as long as you write the code, to the visualization tools that are already in existence and already have this unified data model. And so we started to make that actual structure. When I talked about this last year, it was all this. It had all just really begun, but we hadn't made significant progress. And now, so we can now call up the Firefly tools from a Python command. This is an actual Python prompt, and up come the visualization tools in a separate web browser. But we've also made the next connection, which is now the visualization tools can be embedded within the Jupyter notebooks. And so we've started to connect these widgets between the Python and the JavaScript APIs to be able to blend the two pieces together, and depending on what you want to do, be able to put it together. And then finally, we've made the connection between Firefly, the visualization tools, and Python sharing their data. So if you look closely, these tables are exactly the same table. One is a Firefly table, one is an AstroPy table. You make a change in one, it gets reflected in the other. We've included mask overlays, which is a new functionality. Michael's going to shoot me off the phone here, so I want to get to this last little bit, which is the prototype data access center. So we don't want to build the whole thing and then deliver it at the day of commissioning, right? That is a bad idea. So we're going to develop a prototype data access center where we're going to put data in and we're going to slowly build up our functionality. And the first version of that is going to include Stripe 82 data. It's supposed to come out this year. And then next year, we will include WISE data, which is all sky and time domain. And we'll slowly build up the functionality of the prototype center leading up to commissioning and science operations. At the end of the day, this is an engineering facility, but we do want scientists to be involved in this and accessing this data. So there is a data access policy that's been written. And so you can talk to me more about this in detail. We don't want 500 astronomers trying to do all their science and inundating with the questions and then complaining to us that this particular functionality died because it went away last week. And right, at some level, this is an engineering facility, but we want real scientists poking, trying to do real science so that we can start to build this up. And as we get to commissioning, that we actually have a functioning data access center. So if you have more questions about this, please come and talk to me, and I'm going to stop there. I'm not going to even talk about the summary. I apologize, Jonathan.
That's it. I think follow-up for Jonathan. Any quick questions?
Sorry, Michael. So in general, yeah. I mean, so for example, we've been talking. So in general, yeah. So in general, yeah, we've been talking. So for example, we've been working with the Jupyter Notebook folks to how to do this and organizing that. And so we've been going to SciPy. So there's a variety of places, absolutely. And what we also do is we're gonna, as we develop this, we're gonna put it back into the Infrared Science Archive at IPAC as well. So there is a variety. And you know, we're not the only ones who are doing this kind of, you know, Data Labs at NOAO has something very similar. Sky Server for out of Mass. So this is a common thread that you're starting to see the archives go down.
Let's thank David again. I'm going to talk about documentation.
Yes. So my colleagues have given you a great overview of the data management system, and I hope we'll have lots of conversations between you and the science collaborations and our team throughout the rest of this workshop. But what happens after this workshop, when you go back to your home institution? How can you continue to learn about data management and engage with the data management team? And so that's where this talk comes in. I'll be providing you with some resources you can use to continue to engage with us in the long term. And I'll also be providing you with some ideas about how you might adopt some of the platforms that we're building to communicate with you, but actually within your own science collaborations. So that's what I'll do in this talk as well. So as Andy mentioned, starting with the basics, there are two major documents that are relevant to the people in this room. It's LDM 151, the applications design document, which describes the pipeline algorithms that we've already talked about, and the data products definition document. And so you can just go to those URLs and just, in general, be familiar with those documents, because they answer a lot of common questions you might have. Now, a really exciting resource is the LSST Community Forum. So I encourage you right now, let's crash the Wi-Fi, go to community.lst.org. And this is a site that we launched just 1 year ago at the Bremerton workshop. And already we have 280 of you registered on the forum. And we've had, last time I checked, 680 conversations happening on the forum. So it's really taking off in the past year, and we expect it to become a much bigger thing in the near future. Now, if you go to the community forum right now, it might look a little intimidating because there's conversations happening from all corners of LSST. So one thing you can do to sort of pare down those conversations and have a more streamlined, curated experience is just look at individual categories one at a time. So when you're on the site, you can click on the categories button or the categories dropdown and just look at one segment of LSST that you're interested in. So I'll talk about what some of these categories are. So one is the support category. So in data management, we're providing software that you can use to process data right now. The simulations team also has a metrics analysis framework that you can use to do cadence studies. So as you're getting started using the software, you may have questions. And so feel free to post those questions on the support category. And the actual people who wrote that software are there to answer your questions. And in the long term, that support category becomes a really useful knowledge base where we have, questions that have already been answered. So you can just browse that category to get, really good information. There's also the data management category, of course. Data management is a really open organization. We have a lot of our technical conversations just out in the open on this data management category. So I encourage you to listen into our conversations there. And when there's something that's relevant to your science, feel free to reply to a post and say, for my type of science, it'd be really useful if we could do, this other thing. And also feel free to just, create new posts in data management asking about what we're doing. This is a really great place for you to engage with us, at any time throughout the year. Now, in a lot of these posts, it's kind of small here, but you might notice there are little tags under the titles of topics. And one of the really useful tags is DM-highlights, which is on the next slide, and you can get directly to it with this URL. What the DM highlights are is every week, one of our team members, Tim Janess, puts together a curated summary of the major pieces of work we've done. So features we've merged into master, documents we've released, decisions we've made through our decision process. And he's curated a summary of all the things we've done that week. So it's really easy just to follow this one tag to see what we're doing on a week-by-week basis. Now, of course, a lot of you are interested in cadence studies with the simulations group. So the simulations group has their own category. And so I encourage you to interact with them there as well. And finally, as Lucienne mentioned, there's a science category. And this is new. And we really see this as being your space in the community forum to talk about scientific things related to LSST. And in fact, we're hoping that science collaborations might want to adopt it more formally for their own uses. So we're really interested and excited to see where this goes. Now, the LSST Community Forum is something you can browse without signing up. It's just open, visible on the web. You can Google it, for example. But things get a lot better once you sign up. So I encourage you, while you're at your computer right now, just sign up, create an account. And you can do things like create posts and reply to other posts and have conversations. But you can also curate and customize your experience with the forum to make it a lot more effective for your own uses. So for example, one thing you can do, whenever you go to a category view, look for the circle icon in the top right, and that will let you subscribe effectively to different categories or even mute ones you're not interested in. So you can do things like every time there's a new post, send me an email. So you can customize things like that to keep on track of what's happening on community. Another thing you can do is, that's not noticed often, is you can go to your user avatar when you're logged in and find this gear icon to get to your settings page. And that will allow you to customize a lot of settings. So things like how often the forum emails you, you can customize that. One of the really great things about the forum is we'll actually, if you haven't been on it for a few days, it can actually send you a summary of what's happened, just to keep you on, up to date with LSST. And you can customize how that works with the settings page. Another thing that we started to do in the last year in data management is a thing called technical notes. And these technical notes are standalone web pages we publish to these lsst.io domains. And you can find a listing of the ones we've already published at this short domain, lsst/nre. And what these are is they're essentially short little papers to quickly communicate different experiments we're doing with data and algorithms, design proposals, implementation, details of back-end infrastructure. So things that aren't normally papers, we're just trying to quickly communicate these things both within our team and also to the community. And one of the really exciting things is that soon these will be listed on ADS. So if there's something that's relevant to your science, you'll actually be able to cite that directly from your paper. And I think that'll be really exciting for the future of astronomy literature. So I'm just going to show you the titles of some of the tech notes just to show the breadth of information you can find in these. And again, I'll show you a link at the end where you can find all these. So we have lots of things about diverse topics. So you can go to pipelines.lsst.io, and this will be essentially the future home of the science pipelines documentation. So the things that we've been talking about previously you'll be able to get user guides for actually using our pipeline processing software from pipelines.lsc.io. So right now we have installation documentation, and soon we'll be incorporating API documentation and then fulfilling it out with user guides and tutorials so that you'll be able to get started with our software with existing data already. And this is actually the software you'll be using, in level 3 processing as well, by the way. Another useful website is developer.lsc.io, and we put a lot of effort in this site into articulating just how the data management group, which is composed of about 70 people, all collaborating on software, it articulates how we collaborate together. So you might just want to look at this website and maybe incorporate some of these ideas into your own collaborations if you're working on code together. So we have things like coding style guide, collaborative processes on GitHub, and development tips and so forth. So I want to close out the talk and let you get to lunch by just seeding you with a couple ideas for things you can actually do to leverage within your own science collaborations. So there's 2 ideas I'll give you. One is to set up a category for your own science collaboration on Community and sort of adopt it as a tool for your own group. Another idea is to take advantage of some of the tools we're using for publishing documentation, this thing called LSST the docs. And those are both things that I'll talk about in a second. So with the community forum, you sort of have 2 options, and you can actually do both for your science collaboration. One option is to create a public category where you can essentially talk about your science and even make announcements to the wider community. And you can also create private categories. And these private categories are places where you can have internal conversations within your science collaboration, within your science team, about what you're doing. Now, you may already have things like wikis and mailing lists for this exact purpose, and this slide explains why I think the community platform, which is powered by the Discourse software, may actually be better for enabling these types of conversations over remote groups. So you get things like, really rich formatting. You can write in Markdown, so nice headers and lists. You can even render LaTeX maths. You can actually have really articulate conversations about calibration pipelines and so forth, on the community forum. There's a really great coding system. As you're replying to someone else, you can just scroll up and highlight someone else's text, and it will automatically be quoted in your own post and then linking back to that original conversation. So you can actually have long-lived conversations that are easy to keep track of, more so than in an email thread even. And one of the really amazing features about the community forum is it has amazing on-site search and browsable archives. So over the next 5 years, you'll be onboarding people into your science collaboration, and you want them to be able to read about the conversations you've already had so they know the context of your science collaboration. And so I think this ability to browse the archives is really, really powerful. And as well, it's Twitter-like, so you can mention team members, make sure they're part of the discussion if you think they should be there. Now, in terms of setting up a private category, this is the recipe for how you can do it today. So essentially, talk to me right now, or you can email me, jsick@lsst.org, and I'll set up the category for you. And then I'll also create a group. And with this group, I'll tell you how you can add members. So this will allow you to essentially maintain your own membership list independently of data management. So you can essentially run this category on your own. So it's a really easy process. And then finally, there's also this MailBot service that we have. So we recognize you might already have a mailing list. And what the MailBot does is it can take posts on your new community forum category and forward the content of those posts to your existing mailing list with a link back to the community forum. So this is a great way of just transitioning people seamlessly from the previous context perhaps onto the community forum. And this has worked really well for data management, by the way. And finally, the last thing I want to touch on is LSST the docs. And this is what we're using to publish all of our documentation within data management. You may have seen a lot of these something.lsst.io domains, and these are all powered by LSST the docs. And what this platform does is it lets you write your documentation collaboratively as GitHub repos and then publish them up to the web seamlessly. And one of the really exciting features about LSST the docs is that every single branch and tag in your GitHub repository is published side by side. So if you've used GitHub before, you may be used to using pull requests to collaborate on new additions to your documentation, or even an academic paper. And what this lets you do is actually see that published to the web rather than having to look through the original markup source. So this is what we're using in data management, and I invite everyone here to actually use this, perhaps for your own documentation within your science collaborations. You can even publish things like LaTeX papers on LSST the docs as well. It's a really flexible platform. I don't have too much time to talk about it right now, but I invite you to just grab me and I can set you up. So I'll close out by giving you a list of all the links that I've described in this talk. And so again, these are really great resources that once you go back to your home institution to keep up with data management. And again, I encourage you to think, if you're running a science collaboration, to think about these two options for using community for your own work and publishing with LSST the docs. So thank you very much for your time, and I'll take your questions.
Waiting, of course, for right out of time. Any burning questions? Or if not, we can grab Jonathan and all. Yeah, right.
So, my burning question is, there are all these great tools, but things seem somewhat fragmented.
Yes.
It's difficult for the collaborations to know exactly where to go to get what piece of information. So, do you have any suggestions about the hierarchy of where to look? Or is there...
Right. So there'll be a twofold solution to that. One thing is we're hoping to link to more things on the community forum. Just by following that, you'll see links to more things. The science pipelines documentation, I think, will sort of become a home for a lot of what DM does. So you get links to more resources there. But the real solution in the long term, and my manager didn't want me to talk too much about it because we haven't fully planned this out, is a thing called the documentation hub. And what this will be, and it will probably happen next year, implementation-wise, is essentially universal search for everything in LSST. So we'll be incorporating, you'll be able to search across all the community posts, all of our JIRA tickets, our papers, all of our technical notes, software code. Essentially everywhere we have pieces of information, we'll be able to search it. And with metadata, you'll be able to facet that search according to who's involved in that project, what type of project it is. And we're hoping that even things from the science collaborations can get linked into that sort of universal search. And so this is something that we're really excited to do. We haven't started working on it yet, but it's in our plans. And I think that will be long-term, like by next year, the solution to all this. And in addition to search, it will also be a curated listing, so you can actually browse different resources in addition to just searching full text.
Okay, I would like to close this session. I'd like to thank all our speakers. And my nose tells me and my watch tells me that it's food outside.